Hey there, and welcome to This Explainer. Today, we're taking something you've probably seen hanging on the wall of literally every science classroom you've ever been in, and we're going to completely transform how you look at it. You see, the periodic table isn't just some boring, rigid grid of letters to memorize. It is, quite literally, the ultimate, brilliant cheat sheet to the entire universe. It's a map of everything around us, and I am so excited to finally show you how to actually read it. Here's the roadmap for our explainer today. We'll start by sorting out elemental chaos. Then we'll check out the modern periodic blueprint. After that, we're navigating the chemical neighborhoods, decoding the periodic trends, and lastly, we'll look at the table in real life. Let's dive right in. All right, kicking things off with Section 1, sorting out elemental chaos, the early map makers of chemistry. So let's set the scene for a second. Imagine you're a scientist a couple of hundred years ago. New elements are being discovered left and right, and honestly, it's absolute chaos. Early scientists were completely overwhelmed, and they desperately needed some kind of organization system. And what we see here is a really rapid evolution of chemical thought. In the first phase, we have Johann Wolfgang Dober-Reiner. He noticed these little groups of three, he called them triads, like lithium, sodium, and potassium, that all behaved surprisingly similarly. But, well, that only worked for a few elements. Then John Newlands comes along with his law of octaves, suggesting that every eighth element had similar properties, kind of like musical notes. Pretty cool, right? But again, it really only worked for the lighter elements. Finally, in the third phase, Dmitry Mendeleev steps up. He organized the elements by their atomic mass, and this is where things get truly brilliant. Because the absolute genius of Mendeleev wasn't just that he organized what was already known. The crazy part is that he left literal blank spaces on his map. He knew his table was incomplete, and he perfectly predicted the existence and the properties of undiscovered elements. He basically stood up and said, hey, there's an element missing right here, and when you guys finally find it, it's going to look exactly like this. And you know what? He was right. Elements like gallium, germanium, and scandium were discovered much later, and they fit his predictions perfectly. His table wasn't just a filing cabinet. It was a powerful predictive tool. Moving right along to Section 2, the modern periodic blueprint. Henry Moseley's atomic number revolution. Now, as amazing as Mendeleev's table was, organizing everything strictly by atomic mass had a few, well, hiccups. Like, where exactly do you put isotopes, or hydrogen for that matter? That's when Henry Moseley sparked a total revolution by shifting the focus to the atomic number, which, if you remember, is just the number of protons in an atom. This shift led directly to the modern periodic law, which formally states, properties of elements are periodic functions of their atomic numbers. So what does it actually mean for us? In simple terms, if you arrange elements sequentially by how many protons they have, their chemical properties start to repeat in a totally predictable periodic pattern. It's a remarkably simple rule, but it perfectly brought order to all that elemental chaos. 118. That is the total number of currently known elements that make up our modern periodic table. Just pause and think about the sheer scale of that for a second. Every single physical thing in the known universe, from the most distant stars in the sky, right down to the screen you're looking at right now, is made entirely from combinations of just these 118 building blocks. Now, to understand how to actually read this incredible map of 118 elements, we really need to grasp the difference between periods and groups. It helps to think of the periodic table like a giant city map. The 7 horizontal rows, those are the periods, kind of like streets. They represent the number of electron shells an atom has. Then you have the 18 vertical columns. Those are the groups, and you can think of them like avenues. Elements living in the same group share the exact same number of valence electrons. You know, the electrons hanging out in the outermost shell. And because of this, neighbors in the same group act a lot alike. They share very, very similar chemical properties. Which brings us nicely to Section 3, navigating the chemical neighborhoods, blocks, metals, and noble gases. So now that we know how the streets and avenues work, let's explore the 4 major blocks, or districts of our map. These are organized by how electrons actually fill their orbitals. Over on the far left, we've got the S block that covers groups 1 and 2, and it's home to our highly reactive metals. Jump all the way over to the right side, and we hit the P block, spanning groups 13 through 18. This is where you'll find nonmetals, metalloids, and halogens. Then, taking up that large center section is the D block, groups 3 to 12. These are the transition elements, pretty famous for making beautifully colored compounds. And finally, parked all the way at the bottom like the special annex district is the F block, the inner transition elements we call lanthanides and actinides. Let's zoom in on a very specific neighborhood inside that stands block for a second. Group 1, the alkali metals. Our sources provided this incredibly fun mnemonic to help remember them, and it goes, "Little naughty kids rub cat's fur," which of course stands for lithium, sodium, potassium, rubidium, cesium, and francium. These guys are incredibly soft and highly, highly reactive metals. You absolutely definitely would not want to build a house out of them. And seeing that really helps build our understanding of the two main types of elements we're dealing with here. Metals essentially live on the left side and in the center of our map. They're highly conductive and they absolutely love to lose electrons, making them electropositive. Non-metals, on the flip side, live over on the right. They have low conductivity and they love to gain electrons, which makes them electronegative. And sitting right smack on the border between them, those are the metalloids, like silicon, which creatively share properties of both. All right, into section 4. Decoding the periodic trends. Reading the map's hidden directions. Now, this right here is where the periodic table turns from a simple reference map into almost a literal crystal ball. Because once you know the hidden directional trends built into this grid, you can predict how any element behaves just by looking at where it lives. Let's decode atomic size, for instance. That's the distance from the nucleus to the outermost shell. Step 1. As you travel across a period, from left to right, the atomic size actually decreases. Sounds backwards, right? But it happens because the nuclear charge is increasing, which pulls those electron shells in tighter. Step 2, as you travel down a group from top to bottom, atomic size increases. Now that is much more intuitive because as you go down, you are quite literally adding more and more electron shells to the atom. So the absolutely crucial takeaway here is how character and reactivity flow across the whole board. Step 1, metallic character and the reactivity of those metals increases as you move down a group. So for example, potassium is way more reactive than sodium. Step 2, non-metallic character and ionization energy, which is just the energy required to rip an electron away, increase as you move across a period, from left to right. And these trends directly lead us to one of the most important concepts in all of chemistry, electronegativity. It's basically defined as the tendency or ability of an atom to attract shared electrons toward itself. Think of it as how greedy an atom is. And the undisputed heavyweight champion of the entire table, fluorine, sitting right up near the top right corner, it is the most electronegative element there is. It is incredibly, incredibly greedy for electrons. Finally, we arrive at section 5, the table in real life, from the lab to your living room. We've been talking a lot about theoretical chemistry, protons and electron shells, but I want to remind you, these aren't just abstract letters on a page, they are your actual physical reality. Oxygen, you're literally breathing it right now to stay alive. Iron, it's the structural backbone of the very buildings we live and work in. Copper, it's the vital wiring that brings electricity into your home. And silicon, it's the essential metalloid inside the computer chips powering whatever device you're watching this explainer on right now. And the impact, of course, goes way, way beyond individual household objects. Entire, massive global industries rely completely on the predictable organization of this table. The chemical industry uses it constantly for material selection and designing new alloys. In medicine, we rely on it for radioactive elements and incredibly precise drug chemistry. Electronics, they rely heavily on semiconductors. Modern agriculture depends on specific elemental crop fertilizers. And nuclear science utilizes heavy elements like uranium and plutonium. The periodic table is, without exaggeration, the blueprint for modern human civilization. So, we've gone all the way from the chaotic early days of elemental discovery to a perfectly ordered, beautifully predictive map of the universe. But here's the thing, science is never truly finished. With 118 elements currently known, I want to leave you with this provocative thought. What hidden properties and revolutionary uses will the elements of tomorrow reveal? The blank spaces of Mendeleev's time might be filled, but our understanding of what these elements can actually do together, that is just beginning. Thank you so